Assalamualaikum warahmatullahi wabarakatuh. Ladies and gentlemen, dear everyone, welcome to our tutorial session. My name is Idam Ananta. I'm a lecturer and researcher at Department of Computer Science and Electronics, Universitas Gadjah Mada. We're supposed to meet here in our beloved city. However, with the COVID-19 pandemic situation like this, I think the online session will be the best we can do here. I would like to take this opportunity to talk to you about the story of end-to-end deep learning approach for autonomous robot. The purpose of this tutorial is to share with you our early experience, hands-on about the approach, to see how it works and how good it is in a glance. After this tutorial, I hope you get a better concept, better insight about this approach and a good place to start. So here's the overview. I'll start with the end-to-end deep learning concept. What it is, what is the benefit, what is the consequence, and then I'll try to demonstrate how an end-to-end deep learning works. Start with how to get the data, how to pre-process it, how to build a model based on it, and how to test the model to see how it works. And at the end, I'm gonna share with you some of our early thoughts, and hopefully we're going to have a good discussion afterward. In the case of autonomous robot, for example, usually we have a set of sensors like camera, lidars, gyroscope, accelerometer, etc., and actuators like set of motors. To make this robot achieve some level of autonomy, we usually develop an object detection mechanism. Usually it works with those sensors. Using camera, for example, we might develop some clever image processing so that the robot might be able to detect, recognize, or even track moving objects. Next, we still need to devise a method to assess the situation of the robot itself. It needs to know what it is it in danger, or maybe somehow causing danger to others. Or maybe, at some case, it needs to predict what happened next. When it knows its situation, it also needs to plan forward for what it has to do. Does it has to move forward, doing some evasive maneuvers, pick something or else? And depending on its sets of actuators, it needs to map the planning into the control when it has to deal with set of actuators that the robot has. So it's quite complicated, and sometimes, or maybe more precise, most of the time, it is a troublesome process. So, what an end-to-end learning approach does in this scheme is reduce those handcrafted complexity into a mapping from one end, which are the set of sensors, to another end, which are the set of actuators, using a single neural network representation. Yes, I know, especially for you that not familiar with this method, you might wonder, seriously? Well, it does seem like an oversimplification. And to believe such system is working might be even harder for those who spent many years of their career engineering individual steps of the pipeline, such as object detection, collision avoidance, path planning, etc. They might already wrote multiple papers, developing tools and or libraries, and has significant recognition or income or both from those works. And these methods kind of like saying, okay, we probably don't need those anymore. Nevertheless, one problem that gets in the way for any end-to-end learners is the fact that it needs a lot of data, tons of them. It might be easier to develop end-to-end learning in translation system, for example, because there are a lot of multi-language datasets out there available. In the case of autonomous robot, it doesn't seem the case because going out there many times with the robot collecting tons of data will be very expensive and time consuming. So it's is it the end-to-end learning unlikely for autonomous robot? Well, not really. What if they are able to generate their own data? What if they are able to develop a simulator and let it collect data for you? Recent development in computer technology is not only about computing power, but among other things, is the development of virtual worlds. There are numerous photorealistic virtual worlds around us, and it doesn't take too long for a group of researchers to develop a simulation engine for autonomous project to generate the data and the environment needed. And these are some of them. Okay, so what I want to share with you today is our early experience working with the AirSim. So AirSim is another good simulator to develop, among other things, the end-to-end deep learning. It is developed by Microsoft. It is open source and freely available for everyone. It's built on Unreal Engine, and it also has an experimental version on Unity. You can get it from the GitHub here. So if you click their GitHub site, then I think you have all you need to start with the AirSim simulators. And they also give you some kind of introduction to the autonomous driving. They call it the autonomous driving cookbook. It is a very good place to start, so we highly recommend this cookbook. And actually this tutorial is largely based on this autonomous driving cookbook, so we would like to thank Mitchell Sprint and also Aditya Sharma as the authors, because they are they have inspired us to try this platform and get better understanding about the concept of end-to-end deep learning. And this is the plan that we're gonna do today. So the first, we like to generate the data set, and second, we will pre-process the data and then we train the pre-processed data, and the last thing is we try to test the model that generated from the training. So it's like usual supervised learning pipeline. And this is what you need. We highly recommend you to create your own environment here. You can use the Anaconda. We're using Python 3.6 and any other library here that you need to install before you start. And well, honestly, I think you're gonna face some kind of compatibility problem because the library is keep updating. But I believe you're gonna be okay after visiting some of Stack Overflow pages. So so I think you don't have to worry about that. And you can also download the simulator package. So basically IRSIM has the environment and also the simulator package. If you want to work with the autonomous driving cookbook, you can use the simulator package, but the one that they keep updating is the other one, the environments. And you can also download the data set if you don't want to generate data by yourself. If you don't want to create or driving manually to create the data set, then you can just download the available data set from the AirSim just to look at how it works, how to train the data, and how the resulting model can perform. So it's optional actually. And well, the last thing is that decent GPU and also a bigger RAM will help you a lot. Okay, let's look at the neighborhood environment. So as you can see here, it has wide roads and yeah, some intersection. It is also a static environment. There are other cars here, but they are not moving, so you don't have to worry about them. Of course, at some point they might be considered as obstacles on the side of the roads, but it's okay. We'll see how the end-to-end learning deal with them. We can use the keyboard like I do here to drive the car. Use the arrow to move the car forward. Brakes, turn left, turn right. So pretty much I think it's wait a minute. Okay, it's still running. Okay, so bottom line is you can use the keyboard to control your cars. However, one technical note that you need to consider is that you need a decent steering wheel or joystick to get better data. Previously, we used keyboard in our training, but after generating quite a lot of data, we realized that keyboard only has a discrete steering angle. So if you look at the up left of the screen, then you'll see that the steering is from minus half to one half. Minus half to turn left and a half to turn right. So It's I think it's a discrete. But if we are using a joystick here, let's see if we can have a continuous steering angle. Okay, so if you look at the left side of the screen, then you will notice that the steering angle is also continuous. Well, it's quite difficult to control the car using a joystick if you're not used to. But yeah, I think the ideal uh, device will be a steering wheel. So in this demonstration, we're gonna use this joystick, and we're gonna deal with the complexity. Okay, next you can toggle the depth camera by press 1, or the segmentation camera by press 2, and press the 3 for the RGB camera. This is an important feature because we will work with the image. So good news is we can easily record our image along the way just by clicking the record button, or simply press R on our keyboard. Okay, let's try to record some of our movement. I press R button in the keyboard now. Okay, recording started, and okay, let's do this. Okay, so yeah, it's a bit of difficult to write with this joystick, but yeah, we can still do this. Okay, hit, and let's stop the recording. We can find the recorded image these folders, documents, and RSIM, and you can pick the last one. So here is your image. So I think it's quite few images we have here. And the good news is that the RSIM also save our steering behavior. So like this. So it has like a timestamp, the location of the cars, the throttle attribute, steering, brake, gear, handbrake, RPM, speed, and image file. So it has quite a big data here. So that's how you record the image and the steering behavior. Before we continue, I need to emphasize that the fact what we're going to do is a very simple end-to-end learning. So the objective is simply to keep the car on the lane, on the road, and we're gonna see this as a problem of regression using a CNN with a set of images from front camera and the vehicle's last known state as input, and the angle of steering wheel as an output. So first we need to take a look at how we drive around. The intuition is if we drive carefully. Let's start from the beginning. If we drive carefully, then the car will follow. Hopefully it somehow imitated our driving style. However, it's not enough. An end-to-end learning, as I mentioned earlier, doesn't do feature engineering. So the only source of it's learning is that it's a teacher for manually driving like this. So we should provide all necessary information so that the car able to drive by itself. So it's a good idea to teach the car also to take a drastic measure like turn sharply. For that reason, we will do two different driving style. Let's say normal and swerve. So this is the normal style, and this is the swerve style. So you will create kind of oscillation like this. The objective is to teach the car how to turn sharply if needed. So that's how we're gonna do our data generation. So we're gonna do 6 normal style driving behavior and 3 swerve style driving behavior, and save them into different folders. So that's it for the data generation. Okay, so here is the code for the pre-processing step. As usual, we need to look at where our raw data is, and of course also organize them into normal driving style and swerve driving style as well. And next we will take a look at some sample image that we have from our training, or let's just run this file. Okay, so here is the image captured by the car's front camera, something like this. Actually, we only care about the road, the lane. So if possible, removing unneeded portion of the image will reduce our need of computing power. So we're gonna crop some region of interest into something like this. So it's smaller image, so hopefully it can help us to gain a faster learning speed. Next, we also need to take a look at the distribution of the steering angle and also distribution of the swerve and normal driving style. As you can see here, we have like 65% of normal driving style and about 35 to I think 36% of swerve driving style here. Having tried the normal driving style 6 times, for example, and swerve driving style 4 times, maybe, doesn't always reflect the distribution, as it depends on how long we do each of these driving styles. And finally, let's take a look at how many data points that we have to get a better description. So this is the histogram of our normal driving style level distribution. So I think it's around 0 actually, and yeah, it's gonna be a problem for our neural network, since it will most likely recommends or predict 0 steering angle most of the time. So I think we should reduce this number so that the 0 is not predicted all over the time or most of the time. And if we look at the histogram of the swerve level distribution, it's something like this. And then okay, the code will read the data. Basically what it does is try to combine the image and the non-image data into one, and it creates kind of big hex5 files for our data. So I think it reads, yeah, processing data. It took a while. Once you finish, then you will have at least 3 pre-processed dataset in a H5 formats. I think that's it for the data pre-processing. Okay, if the data processing goes well, then you will have these 3 H5 files. It has a very big size. For example, for the training dataset, you have 3.5 gigabyte, and from the eval dataset, you have more or less 1 gigabyte, and half of them for the test dataset. So next step will be to train this dataset to develop our model. So let's read those data and define our dataset. It is too expensive to load the entire dataset into memory, but lucky for us, Keras has data generators. Basically, it's an iterator that will help us read data from this in chunks, so we don't have to put all of them at memory at once. So I think it's the best to do for our situation. And next, we're gonna apply some data transformation to create a richer data. What we're gonna do is try to flip around the y-axis. As the car in neighborhood environment are actually driving on flat environment, there should be no significant y differences. We can also see this flipping transformation as passing the same road from the opposite direction without having to do so. The flipping image, is, I think, is quite easy to do. However, we still have to flip the label as well, as this is a custom requirement. We need to extend the image data generator class here, and we're gonna implement our transformation of the labels manually. Another transformation that might help is to try different lighting scheme. As our car is expected to drive autonomously in different time of the day, if you look at the color feature in the previous video, you might notice that it provides a night simulation. We are not aware if AirSim provides the same capability. In fact, AirSim has ways to get different weather effects like raining or snowing or a different time at the day. However, in our demonstration, we take a different approach. We can randomly set the brightness of the image to simulate lighting dynamics, and we can do that without having to manually driving into different weather or different time of the day in the environment. If we set, for example, the brightness level of our training to 0.4, then the brightness of each image will be modified by up to 40%. To do so, we need to transform the image from RGB to HSV, and we're trying to modify the V scales up or down, and the result we're gonna transfer back to the RGB space. And then the next step will define our network architecture. So here is our network architecture. So we use a combination of standard convolutional and max pooling layer to process the image, and we're gonna inject the last state of the car as additional feature into the dense layer. Yeah, these parameters might not be the best, but we'll see how it works. Okay, finally, let's see how good our end-to-end deep learning is. Please keep in mind that the purpose of our learning model here is simply to keep the car on the road, simply to keep the car on the lane, so as long as possible. Let's start with the imports module here. As you can see, we only need the Keras models to load our trained models, and the other component, the other modules you need here is just like a standard modules, and you need to define this as well to facilitate our connection to the AirSim. You need the AirSim client as well, so make sure that it already in your folders. And then this is the path to the models, and you can put it here, and this is the line of codes to load the models. Next, we're gonna connect to the AirSim simulators. Before you do this, make sure that you open the environment first. So let's open our neighborhood environment. Okay, wait a minute. Okay, here you are, the environment of neighborhoods. And then this is the line of codes to connect to the environment. Next, we initialize some of the car parameters. We also provide with some buffers to start our models prediction. And then we will need the cars in our IRSIM to get the image. So this is how you get the image from the RGB camera from the AirSim. And then yeah, this is where you start the control. So first it will get the image and the state, and it tries to get the output of the models, and it will fetch the steering angle into the car's control. Okay, so that's it. So okay, let's see how it runs. Let's run this Python file. Oh, wait a minute, I need to change this into my virtual environment. Yeah, Skynet. It's that Skynet. Yeah, we have. Oh wow, it's running. See, this is the model tracking. Is not me. So yeah, that's our model. Let's see if it can make the first intersection. Can it pass it safely? Can it turn? Oh wow. Okay. Still running, still running, still running. You know what? I think it's pretty good for a very little dataset here. It passed the road with the shadows, and let's see if it can survive the next intersection. Okay, a little bit bump here, and okay, still going, still going. I know you might wondering why the car is doing something like that. Maybe some of you have some kind of hypothetical reason why the car's behavior is like this. Maybe we put too much swerve driving style into our model, so maybe this is the output of the model. So let the models drive our car a bit more, and let's see how far it can go. Still going. It's pretty much. It's going, it's going, it's going. And let's see if it survived the next intersection. Okay, another bumpy turn, but still survive. Another turn. Can it make it? Okay. Okay, what's out of the car? What's out of the car? Wow. Okay, it can handle that quite good. Still going. What's the car? Okay, it hits the first car. So, what do you think? Are you ready to let the end-to-end model take over your car? No? Yeah, me neither. My daughter said no is a big no. And I think she got the point. Even Andrew from Coursera didn't recommend the end-to-end deep learning strategy for autonomous driving. And one might argue that he or she can make a better autonomous robot using more traditional approach, like using an object detection system or collision avoidance system, etc. But to be fair, Andrew's video was a few years ago, and he didn't mention about the possibility of simulators that might help us. And to make another fair point, we only took a very little dataset here. We took 6 normal driving style around the neighborhood and 3 swerve driving style as well. And those are all the data we have. And this car, which learned from those limited dataset, has managed to survive quite a long time. Well, this is not always the case, of course, but I believe this achievement is quite promising. In the end-to-end learning is good as it let the data speak. If it speaks and good enough, it will hopefully capture all the features needed in the right distribution, and it leads to less hand designing of component needed. So it will potentially exclude many useful hand design components such as object detection, path planning, etc. End-to-end learning obviously needs a large amount of data. Simulator will help, but it remains to be seen on how good it is in the real world. However, with techniques such as behavior cloning, simulation result can be fine-tuned using lesser amount of real-world data and used on actual cars. One other problem for this approach is that we can't always explain the car's behavior. It massively relies on the teacher to perform a comprehensive driving style. The other thing we can do afterward is only tune the parameters to hopefully get the best model. There's another techniques like deep reinforcement learning that might help you customize the driving style along the way using reward and punishment mechanism. Interestingly, our model in the end-to-end learning can speed up the deep reinforcement learning training using transfer learning. You can also try it on IRSIM as well, since it also provides the tutorial. So there you are, our experience and I just want to say to you who already mastered feature engineering and other skills on the more traditional pipeline, no need to worry. I believe this is not the end, and the end is not even near. Even in the future, I believe there are so many useful things that we can do with those amazing skill set. And if you are end-to-end early adopter, I know what the temptation is. You don't have to master those individual skills in the pipeline and still hoping for a decent result. What I show you today might be a good place to start. It's not bad, it's promising. The good thing about this is that there are many open questions in this area that your brilliant mind can help. Thank you for watching. That's all from me. Looking forward a good discussion. Assalamualaikum warahmatullahi wabarakatuh.